My name is Jakub Lemisz, and the title of my presentation is Efficient Framework for Operating on Data Sketches. Let me start by identifying the problem I'm solving. The classic problem in the analysis of data streams is to estimate the cardinality, that is, the number of unique elements in a stream. The best known algorithm for this task is hyperlog-log. In my paper, I generalized this problem by adding weights to elements. So each element of a stream has now not only identifier I, but also a positive real weight Wi. The basic scheme for this type of algorithm is as follows. First, we use hash function to get rid of duplicates present in a stream and deal only with the fundamental set. Then we summarize the information about fundamental set in a memory-efficient data sketch. Finally, by using data sketch, we can get estimates for the number of unique elements or sum of weights of unique elements. Let us assume that we have two data sketches A and B generated for two fundamental sets A and B. We would like to use these sketches to simulate operations on fundamental sets. For example, based on sketch A and B, we would like to estimate the cardinality of the union, intersection, and difference of sets A and B. We would also like to generalize our sketch to estimate weighted cardinality. Weighted cardinality of a set is just the sum of weights of set elements. So we would like to use our sketches A and B for weighted sets A and B to estimate the weighted cardinality of the union, intersection, and the difference of sets. The typical use case for such operations on sketches is connected to the analysis of information from many data streams. Namely, we can simulate set theory operations on a number of streams based only on their sketches. In particular, we can ask for the union or intersection of all streams. We can also collect information about different aspects of a given stream in different sketches. For example, if we consider a stream of tweets, we can ask about the set of users tweeting from UK in French at night as an intersection of three sketches. In 2021, I've proposed an algorithm for creating sketches called ExpSketch that is strongly based on properties of exponential probability distribution. The idea is that for each stream element, we make M experiments. In each experiment, we compute the hash of the identifier I and the experiment number K, and consider it as a random variable U with uniform distribution. Then we use inverse sampling theorem to transform this variable to exponentially distributed random variable E with parameter Wi. Then we compare this variable E to the cut position of the sketch and take the minimum. Finally, we get the sketch where at cut position we have exponentially distributed random variable with parameter equal to the weighted cardinality of a stream S. By taking the harmonic mean of all positions on the sketch, we obtain unbiased estimator of the weighted cardinality of a stream S. We also show that this is maximum likelihood estimator, which makes it, in some sense, optimal. For each stream element, we need to generate M random values. And this causes that we need to make exactly M comparisons in line 6 of the algorithm. In this paper, I introduce changes to the algorithm that make it much more effective. The new version of the algorithm is called FastExpSketch. The idea is that we don't need to generate M random variables for each stream element. Namely, we find the current maximum in the sketch and generate the same exponentially distributed random variables as before, but now in the increasing order. And we stop the process when we get a variable larger than the current maximum in the sketch, as we know that this value or any larger value surely won't change the sketch. To efficiently generate exponentially distributed random variables in increasing order, we use recursive formula proposed by Alfred Renyi in 1953. Finally, we compare obtained random variables to random positions of sketch M. As before, we've done this in the line 6 of the algorithm. Okay, so we need to generate the same random positions in a sketch for the many occurrences of a given element. So we do this by using Fisher-Yates shuffle seeded by an element identifier. Note that in the original EXP sketch, we always have m comparisons for each element. So we always have m times n comparisons in total. In FastEXP sketch, the total number of comparisons depends on the value and the order of weights. If the weights have similar value, the total number of comparisons is logarithmic in number of elements n. Namely, we have some number of comparisons for initial stream elements, but for most elements we have 0 comparisons. If the weights grow gradually, the number of comparisons is still logarithmic. If the weights grow rapidly, the number of comparisons is getting closer to bilinear in n. But note that this is a pessimistic scenario. In typical case, when the order of elements in a stream is random, we still have logarithmic number of comparisons. Let us now explain how we make operations on data sketches. Let's start with the basic operations. To estimate weighted cardinality of the union of sets, we use estimator based on the sum of minimums over all sketch positions from k equal 1 up to m. And this is unbiased estimator. To estimate the weighted Jaccard similarity, that is the ratio of weighted cardinality of the intersection and the union of sets, we just compute the number of sketch positions that are equal for all the sketches. And we also get unbiased estimator. To estimate intersection of sets, we just take the product of the union estimator and the Jaccard similarity estimator, and we also obtain unbiased estimator of the intersection. In similar way, we can obtain unbiased estimator for the difference of sets. To see how we can get estimate for any sequence of operations, let's start with 3 sets. First, let us note that any sequence of operations can be presented in disjoint disjunctive normal form, that is, as a sum of intersection of sets or their complements. Namely, whatever operations on sets we do, the result is always built of sum of 7 possible intersections. So let us consider a simple example in which we have a union of 3 intersections. If there is no set complement in the intersection, then we can use the basic intersection estimator. Okay, so this estimator. Assume now that we have a complement of a set C. Then we show that by counting the positions where sketches A and B are equal and smaller than C, we get unbiased estimator for the intersection. Obviously, to get rid this omega from the denominator, we just need to estimate the union of all sets using basic union estimator. Similarly, we can find the right formula for the unbiased estimator for each of 7 possible intersections. We can generalize this scheme for any number of sets. Assume we have sets A, B up to F, and for each set we create a sketch. Let set X be obtained from these sets A, B up to F and some set theory operations. So first, we express set X in a disjoint disjunctive normal form. Next, for each intersection R, we compute the value of the corresponding estimator, where the form of this estimator depends on which set in the intersection we have complement. Okay, so in this case, we have complement for sets D, E, and F. So we have these sets here in the minimum. Okay, so each such intersection estimator is unbiased. So finally, we can sum up all these estimates for disjoint intersection and multiply this estimate by the estimate of the union of all sets to get rid this omega from the denominator, and we get unbiased estimator of the weighted cardinality of set X. And we also know that the standard error of this estimate depends on three parameters: the size of the sketch M, and the weighted cardinality of the omega, and the weighted cardinality of X. So the larger the sketch size M, and the larger is the weighted cardinality of X in respect to the size of the omega, the better, the more precise is our estimation. Finally, let me say a few words about experiments. I test FastXsketch on my MacBook for a stream of 1 billion elements. So when the sketch size M is set to be 1000 and the weights are random reals, I needed 4 hours and 20 minutes to create a sketch. When I increased the sketch size M 10 times to be equal 10,000, time increased to 5 hours and approximately 30 minutes. In a pessimistic scenario, when the weights keep growing, so namely they are consecutive natural numbers, the time increased to 5 hours and approximately 50 minutes. To test the whole framework, I collected a one-day stream of 6 million tweets from Europe, and I created 30 sketches with information about country, language, and publishing time of a tweet. For sketch size equal to 1000, okay, and these 30 sketches with the size 1000 take less than a quarter of a megabyte. Okay, so using these sketches, we can run any query based on set theory operation. So for example, we can ask about what is the number of distinct users that tweet only in the afternoon, and what is their average number of followers. Or we can ask what is the number of users that tweet in Spanish or German or French or Polish, but never write in English. Okay, or what is the number of users from France or Spain that always tweet in English? Okay, thanks for listening.